Welcome to this session. My name is Renee McCormick. I'm the Executive Director of Science Programs for the National Math and Science Initiative, and I'm really glad that you're here. This particular recording is all about AP Environmental Science and grappling with graphics and data, because you're going to be asked to do that quite a bit. You'll be asked to do it in multiple choice format as well as in the free response format of the exam. So we're just going to hit some of the highlights and dust off some cobwebs because along the journey that you have taken to get to this course, you've encountered a lot of these skills before. It just may have been a while. So I remind you that you're not going to have a calculator on the actual exam, but we may need one from time to time as we go through some of these examples because I pulled examples from real life. And so I didn't rewrite them to make the math super easy, but you know that that's going to be the case on the actual AP exam. So let's dive in, get started. The sooner we start, I know, the sooner we'll finish. So part one, data, data tables, and graphs. Well, you're going to be asked to construct data sets, and you're going to be asked to graph those data sets onto a set of axes, or a bar graph, also known as a histogram, etc. So you'll also have to interpret graphs where they've given you the graphic, and you'll have to work backwards from it and deduce what's been going on with the trend in the data and use it to maybe even predict. And when you predict, the most common ways that you do that is you either do it within the data, which we call interpolating, or you do it outside the data range, which we call extrapolating, going above and beyond and going extra outside the data. So when you're analyzing data, you always have to contemplate the independent and dependent variables. Now, you have probably had, I don't know, 4 or 5 at least science teachers by the time you have arrived here. And I suspect each and every one of them has had a different way of trying to explain to you the difference between independent and dependent variables. And I'm just going to confess now that I struggled with that as a student myself. So once upon a time, I was doing a workshop with a bunch of teachers, and it was what we call a vertical team meeting where we have teachers that teach 6th grade on up through AP courses. And one of the middle school teachers enlightened me with one of the most clever things I've ever seen about graphing for students, and I've loved it, so I've adopted it. And it's called dry mix. And so you see this picture over here on the right hand side of your screen where we have the y-axis and the x-axis and the words dry mix, which stand for, it's an acronym of course, and it stands for the dependent for the D in dry, or the responding variable is plotted on the y-axis. So dependent or responding variable goes on the y-axis, while mix stands for the manipulated, meaning you're designing it. I want to take a reading every 5 minutes. I'm going to take a mass measurement every 1 centimeter of growth. That sort of thing. It's the manipulated or the independent variable, and that's going to be plotted on the x-axis. So let's go through a few examples where we kind of read through a little scenario and try to figure out what is the x and what is the y in the scenario. So let's practice with a couple of examples. If a scientist conducts an experiment to test a theory that a vitamin could extend a person's life expectancy, take more vitamin C, take it in such a dosage, and you'll live longer type thing. Then the independent variable is the amount of the vitamin. The experimenter is actually manipulating that. So it's being manipulated, it's independent, it's the M and the I of mix, so it goes on the x-axis. Then the dependent variable is the one that is being affected. And notice affected with an A. A is the action verb, E is the noun, so effect versus affect. So this is being affected by the independent variable. In this case, then, that would be lifespan. All right, let's try another. A scientist studies the impact of a drug on cancer. Well, again, the independent variable is the administration of the drug, or the dosage of the drug. How often do you get it? How much do you get? Etc. The dependent variable is the impact that the drug would have on the cancer. However, you can measure that. Reduction in the size of a tumor, maybe slowing down the mitotic rate of the cell division inside a tumor, etc. So maybe third time will be the charm. A scientist studies the impact of withholding affection on rats. You know, they're adorable creatures. So the independent variable is going to be the affection, because that's what's being withheld, that's what's being manipulated. But the dependent variable would be the subsequent reaction of the rats to that deprivation of affection. Or a scientist studies how many days people can eat soup until they get sick, meaning not nutritious enough. So the independent variable is the number of days of consuming soup, and the dependent variable then is the onset of any illness from that. So you just have to practice. I suggest, if you're still struggling with that concept, that you get out on the internet. You know that new thing called the internet. Get out there and look for more examples of independent and dependent variables, and just read scenario after scenario until you get the hang of it. If you've listened to me much before, you know my philosophy about learning. We're all capable. It just comes down to the number of repetitions. So you may need more examples than what I gave you, and that's okay. Now, in mathematics, you've been dealing with x and y for a very long time, since you very first learned to plot points. Do you remember ordered pairs? X, comma, y, where this might be 1, comma, 3, and then you go to a set of axes, little graph paper kind of thing, and you've made a scale, and you've figured out the scale by hand and all that sort of thing, and now you can start plotting points where you would go 1 unit over on the x-axis and 3 units up on the y. Because these are both positive numbers, you'd go to the right and up, whereas if they were both negative numbers, you would go down, and you would also go to the left. So you go to the left for the x value, and then you go down for the y value. All right, so when we graph these, when we talk about it in math class, they often call them variables. Well, that's why we talk about independent variables and dependent variables. So we have this lingo, in line with what you're used to in math class. So if an equation shows a relationship with which, let me try that again. If an equation shows a relationship between x and y, in which y is specified in terms of x, then y is known as the dependent variable. And so sometimes it's referred to as the function of f of x, or you may have seen this shorthand, the f of x. The final solution of the equation, y, depends on the value of x, which is the independent variable, which can be changed. So for those of you that prefer mathematics, those two definition bullet points may be more helpful to you. But either way, never ever forget that the slope is calculated most simply by a change in y over a change in x, which was probably first introduced to you by some gifted math teacher back in elementary or middle school, and when they called it rise over run. And so you'll hear me say rise over run a lot. I say it even in AP Physics because it's kind of where you filed that first in your brain, and so I'm always trying to trigger where your memory is stored in your brain. And so the algebraic sign of the slope has meaning as well. This is a decreasing slope. So if time were on this x-axis in particular, as time goes by, whatever was happening was decreasing. And then, of course, the opposite to that would be an increasing slope. As time goes by, whatever we're measuring has been increasing. So slope has meaning. If this was mass and this was volume, then the slope would be equal to mass over volume. And I'll bet you know that relationship. What is the relationship between mass divided by volume? Yep, it's density. So never underestimate the power of the meaning of slope. All right, so generally these graphs are going to be line graphs, and they're going to include information collected within a given period of time, which is really good news because any time you see time on the x-axis, you are in the land of rate, and you've been solving those kinds of problems for a lot of years. So if the line on a graph is a straight line, the slope is simply equal to the rate. So if it's a straight line, then it's got a constant slope, and that means that the slope is the rate. A real quick calculation to be able to determine that from a graph. If the line, that says it, I need to fix that, sorry about that. If the line is a curve, then you're asked about rate at a given set of conditions represented by a point on the graph. Now you have a new technique. So forget the mass of the volume. We're talking about time being on the x-axis. And so as time goes by, if this occurs, that's not a straight line, agreed? But they ask me about time 10. It could be minutes, seconds, hours, years, centuries, millennia, your choice on the time unit. But let's say it's 10. Then I simply come up to my graph, I draw a point at that exact time, then I lay a straight edge down next to it, so I'm a freehand in this, won't be as pretty as what you could do. And you draw the line, the one and only line, that by definition is tangent to that blue point on the curve. It touches the curve, in other words, at that one and only one point. And then you do your rise over your run thing, and you calculate the slope of that line. So the slope of that line The slope of line tangent, not the button on your calculator. The line is tangent, snuggles right up to the curve at only 1 point. Slope of that line tangent is equal to the rate. That's what we often call an instantaneous rate. The rate at an instant of time is what that translates into in common everyday language. So now you have a couple of different ways that you can calculate rate, because we talk about rate a lot in this course. You know, the rate of carbon dioxide accumulation, the rate of oxygen depletion, the rate of growth of an organism, rate. So just kind of do a little happy dance when you see time down here on this x-axis, because you get to use those rate tricks to answer questions. Easy points. That translates to easy points. Now, data can also be represented in another way, a logarithmic way. You had a biology course. You learned about DNA. If you got to do any experiments with DNA, like DNA fingerprinting kind of exercise, you may have graphed the data using some semi-logarithmic paper, where we graph out base pairs. So those little stripes of DNA that you see where you get these kind of patterns, these little bandings going on, we actually sit with a ruler and measure these and can graph them, and that's how we determine whether someone is a DNA match with someone else. So we can represent data logarithmically. So a logarithmic scale is one that has a measurement that displays the value of a physical quantity using intervals corresponding to orders of magnitude. Orders of magnitude is big people speak for powers of 10. If I have one of these versus a million of these, which would you prefer? This one is on the order of 10 to the 0, because that's what 1 is equal to when I write it exponentially as a power of 10, whereas this is on the order of 10 to the 6. So these differ by 6 orders of magnitude. And if you've listened to me back when we were talking about scientific notation, that's kind of why we prefer it. Because at a glance, we can tell that 1,000 differs from 1 by 3 orders of magnitude, and 1,000 differs by 3 orders of magnitude with a million as well, because 1,000 would be written 10 to the 3. All right, so orders of magnitude. Rather than a standard linear scale, not everything in life is so simple as that it's just linear, where you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across the x-axis, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across the y-axis. We are big kids now, and so your scale does not have to be a 1-to-1 ratio. So for each unit, then, we may find it's better that to use either on the vertical or the horizontal axis equally spaced increments that are labeled 1, 10, 100,000 instead of 1, 2, 3, 4. So each unit increase on the logarithmic scale, again, represents an exponential increase, or a power of 10 if you prefer, in that quantity. So you already know at least 3 base 10 logarithmic scales. You may not know that you know them, so let's add to your data sophistication prowess. Richter scale. Heard of it? Of course you have. What does it measure? Earthquakes. Says so right here on the page. The Richter scale, and there's another scale as well, but Richter is the one most people know by name. So Richter measures the difference in earthquakes. And then you've also heard of pH, the pH scale for acids and bases. And then human hearing. We talk about measuring things in decibels. So all 3 of these work off of a logarithmic scale. And explain this to people. They don't get it. I wish the news people would actually explain this. When we talk about an earthquake of 3 on the Richter scale compared to a subsequent earthquake of 5, people know that in general sense, 5's higher number, it must be worse. All right, but that's all they really know. They don't know how much worse. They don't understand what that really means. When we say 3 on the Richter scale, we're talking about seismic wave action, and a lot of other complicated mathematics, but let's simplify it and say it's that power of 10. So it's like 1,000. Whereas an earthquake of 5 is 10 to the 5th, which is 10,000. No, that's not it. It's 100,000. 1, 2, 3, 4, 5. Yeah, it's 100,000. So they don't understand that the 5 is not just worse, but that actually it's the difference between 10 to the third and 10 to the fifth, which is 10 to the second, which is 100 times worse. So the same thing goes with pH. When you're comparing acids and you have a pH, because with the pH scale, we have this idea of neutral is 7 in the middle, and then as we leave neutral, it's alphabetical, acid to base. So you get more and more acidic the farther you are at the lower end of 7, and you get more and more basic at the upper end. So if I talk about an acid that, again, has a pH of 5 versus a pH of 3, the one that is 3 is 100 times more acidic. Okay, so that's backwards than what we just said on the Richter scale because of this moving away from neutral direction. The Richter scale is more linear, going solely in that direction. So you have to know a little bit more about how the scale was constructed. Now, why on earth do we care? Why do we want to plot anything logarithmic? Well, you've already seen that earthquakes matter, all right, because the seismic waves are gigantic since they go through our planet. But plotting data on a logarithmic scale has a lot of different advantages. You're going to see it quite a few times throughout the year in different units of study. So the data within a given set may span many orders of magnitude, like I've said. For example, a particular toxin may be given in parts per million. All right, let's talk about parts per million for just a moment. You know about percent. Yes, percent is parts per 100. Now, no one really writes it that way, but it's always how many parts, because a percent is simply part over whole times 100, with 100% being an absolute. It's 100% apple juice. Nothing else is in there. But when we talk about parts per million, it's the same thing. It's parts per million, ppm, and it's simply part over whole times, guess what? Yep, 10 to the sixth, a million. So when we try to do 0.02, 0.31, and 101 plotted on a linear scale, the three smallest data points are going to be all piled up on top of each other, and you're not seeing any separation. So it would be kind of as if those were all equally bad, when in actual fact, that's not the case at all. So it's better to put them on a logarithmic scale. So here is a good example, and this, maybe an example will help, and one you can relate to may help even more. You might accidentally like this. All right, so college students often joke that when a scientist gives a presentation, every mathematical equation shown causes half of the audience to stop paying attention. So every time a math equation is thrown at you, half of the audience stops paying attention. So let's pretend we're at a boring lecture of this type, and the scientist giving the lecture has 15 PowerPoint slides. At the beginning of the lecture, before any slides are shown, everyone in the audience has a great attitude and they're paying attention. Each of the 15 slides does indeed contain a mathematical equation, and each time a new slide is shown, half of the audience tunes out. How many people would have to be in the audience for there to be even one person left paying attention at the end? Well, sometimes you've already seen when we were doing dimensional analysis and such, sometimes it's better to start at the end and work backwards. This is one of those cases. If we're going to have one person left at the end, we know there's 15 slides, and half of them quit paying attention every time, this is a simple doubling, 15 slides worth. So your job is to construct a data table and, generate two graphs of the data, one on a linear scale and another on a logarithmic scale. So be sure to include a title, label the axes with units in parentheses, just good graphing syntax, I guess, for lack of a better word on my behalf. And since you're plotting a discrete data points, please plot them with a symbol and connect the symbols with a line. A dot is a symbol. A triangle is a symbol. A box is a symbol. It's your call. I'm going to use a dot. All right, so what's the first thing we need to do? We need to get this data. So we have 15 slides. So data tables have titles at the top. Slide number is a good title. And then students paying attention. Slide 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Uh-oh, I'm out of the box. 13, 14, 15. 15 slides. We know that 1 is paying attention at the end of that. Okay, so that's 1 that's left. So if half quit listening every time, what's the reciprocal of half? Think about it. Yes, 2. So a doubling. So before that, there were 2 students still paying attention, and before that, there were 4, and then 8, and 16, and 32, and then 64, and then 128. I'm going to slow down here. 256, double that. 512. I know my numbers are going kind of sideways here. Apologies. And then after 512, that'd be 1024. And then double that, 2048. It's a big lecture hall. And then double that, and that would be 4096. And then double that, and that would be 8,192. And then 16,384. Okay, that was more mathematical exercise than I might need. I would double check my numbers if I were you. All right, we need to generate a couple of graphs here. So I'm going to make this nice and big so you can see it. I'm not going to fit it all in this box, obviously. But I'm going to start off with just figuring out what's on my axes and giving it a title. A boring lecture. You could probably do better than that. Number of slides with math formulas. Now, what will that scale be? That's the easy one. We always start with 0 right here. Well, not always, but it's nice to. And we know we're going to be out here at 15. So I would call that about 10, and I would call that about 5. And then 1, 2, 3, 4. I like to make the 5s bigger. 6, 7, 8, 9, 10, 11, 12, 13, 14. It's the best I can do without a ruler and a grid. All right, so that ought to work, right? 15 slides. Yep, got plenty. All right, then what? Well, what's my range? Ranges from 0 on the y-axis to 16,000 some odd. So I'm going to go maybe in 10,000 increments. Would that work? 10, 20, 30. Yeah, that ought to work. 10,000, 20,000. I know you're saying 10,000 what? 20,000 what? I'm getting there. 30,000. What are these? These are number of students paying attention. Okay, so my symbol is going to be a dot. So looking at my data table, at 15 slides, I had 1 person paying attention. So that is just barely above that x-axis. At slide 14, I had 2, also barely above. Remembering that this is 10,000 right here. Okay, so these things are all crowded down here, and it's not really showing much delineation. There's where 4 might be. Here's where 8 might be. Here's where 10 might be. And, I'm sorry, not 10. I did 1, 2, 4, 8, 16, 32. They're all still crunched up here. We're not going to get much toward 10,000 until we get up into the hundreds. So this kind of the point is that you're not getting much separation all the way over until you get to like the 7th slide and you get to 250. So 250 might be more up here. and then a little bit maybe more up here. And then we're going to jump to 500 when we get to 6. So 500 might be somewhere along in there. And then 1,000. So we're 1/10 up on this little slide here. And then 2,000. And then 4,000 would be just under halfway. And then 8,000, we're coming up along here. And then I get to 16,000, which I'm going to say is somewhere maybe about right here. And so it's not real useful. It's not a good scale. So if I draw my line, I get this curve that's coming pretty much down to hug the x-axis. And then you could keep going if you had more slides, and you can extrapolate this on up, but the blue solid line is what I have going on. So that's not all that useful in terms of, if they asked you a test question, they plotted the data this way, you'd be going, well, I don't know what answer to give you. They're all laying them back down there on the x-axis. There's hardly any way for me to read this graph. Well, therein lies the reason that we sometimes go to a more logarithmic distribution. So I'm going to get myself a little extra room. And we're going to try that again using a logarithmic scale. Now, because I'm lazy and have short-term memory issues, I'm going to copy my data, bring it down here in a nice new space, paste it. There we go. Pretty good aim. And I'm going to try this again. This time we're going to use a different scale. Pretend I can draw. All right, what do we have going on the bottom? There's still no reason to change this x-axis. The x-axis, easy for me to say, is number of slides with math equations still. Math equation singular, one per slide. Okay, third time's a charm. Thanks for your patience. All right, we're still going to start with 0. And now we're going to go in elements of like 10, 100. So we're going to go logarithmic. 10 to the first is known as 10. 10 to the second is known as 100. 10 to the third is known as 1,000. You get it. I probably should make a better. 10,000. What would be next? 100,000. And that's as far as I need to go because I top out at 16,000. Okay, so now what happens? Now I need to do the same scale along the bottom that I already had, where this will be like 5, 10, and 15 slides. Okay, so now what happens? Well, go back to your data. At 15, you only have one student paying attention. So that's, I'll do it in purple this time. About right there. And then at 14, I had 2 paying attention. A little higher. At 13, I had 8 paying attention. And at 12, rather, I had 8 paying attention. This would have been easier if I'd have made this pretty, huh? And so at 10, I had 32 paying attention. So my 15, 14, 13. At 10, I had how many? 32. But can you see it starting to shape up to be a bit linear? So then at 9, I had 64. Somewhere up in here. And I'm just going to go ahead and cut to the chase and say at 1, I had 16,384. So that's going to be somewhere along in here. So essentially, if I'll go down another one. Let's get the 3. 3, I had 4,000. So about right here maybe. So you can see that essentially, if I could draw better, this is shaping up to be somewhat linear. So it's the difference between stacking them all up and having a curve and not being able to separate the points as it is to put it together this way. So if you'll humor me for just a moment, I'm going to do it pretty on a graphing calculator. I know you don't have this on the exam, but it'll give you a better representation than what my sad, sad drawings could do. Stat, enter. Now I'm going to put in my 1 through 15. If anyone would ask me, I would have you use the graphing calculator on any science exam. You can use them on all of the science exams, but biology and APES. I cannot explain to you why. All right, so we said at 1, no, I got to do it the other way around. It won't let me. All right, I had written down my data right there. So I'm going to rearrange my windows a little bit here, so bear with me so that I can get to my data. There we go. So I had 16,384, paying attention at that moment. Six 2048 1024 512 256. You could also do this in Excel. You could do this in Logger Pro software, which I hope your school has for you, and a plethora of other sorts of softwares. Four, 2, and 1. Thankfully that worked out. Now hopefully I didn't make any egregious typing errors. Alright, so I need to make sure I have a plot on. I do. I have this one on, and it's going to plot L1 and L2, which is peachy. And so if I go zoom 9, it should make the graph. I've got something in my y equals coming across the bottom, which is not necessary. Clear all that out too, not to confuse you. Okay, so there's what it looked like originally. That's a far better picture than what mine was, don't you think? Don't you think? So now, if you look over at this one, this scale over here, it becomes far, far more linear. And so this is plotting it the way we tried to plot it up here. My graph, ugly. This graph, pretty. My graph, ugly. So when we change the axis and we set our scale to be logarithmic, this is what we get. You've been a good sport so far. I promise this is as ugly as it's going to get. So let's go back and look at the next sort of graph that we need to be able to interpret. Percent change. Percent change is much more easily interpreted. So a change of 7.5 to 10% would be the same distance on a graph as a change to 75 to 100% because they both have a 25% change. So this particular graph about gas prices and vehicle miles traveled was a good example because look at this axis over here on the far left. Note down on the x-axis we have the calendar. As much as we'd like to control the calendar, we cannot. So it's very independent, so it's our independent variable. Starting January 01, going through May of 04. Then we look on the left-hand side and we see that 0 is not down here in the corner. 0 is up here because with pricing, you can have increases and decreases. So you're wise to put it closer to the middle. It's not exactly in the middle, but closer to the middle. So gasoline prices have been going upward steadily probably most of your life. Very rarely do they drop, but when they do drop, it's monumental and everyone does a happy dance. So now we can go minus 10, minus 20, minus 30%, more likely increase of plus 10, 20, 30, 40, 50. But over here on the right-hand side, it's not a one-to-one relationship. You don't have a 1% increase in gas price and a 1% reduction or increase in vehicle miles traveled because you get many miles to the gallon. And so this one is on a totally different scale. It's on a scale of 1/10 as much on the right-hand side as what is displayed on the left-hand side. So now it's just a matter of us doing some simple interpretations. So pause me, take a moment, read the intro, and try to answer all three of these questions. Don't cheat. Put me on pause. You give it a shot. Welcome back. All right, so what happened to gasoline prices in late 2001 and early 2002? And then let's just answer that part first. What happened? Well, first you need to look at the graph. You need to identify that time frame. So late 2001 would be like November-ish of 2001, so somewhere around this range on the time scale. And then early 2002 would go maybe over here to somewhere before April-ish. So we're talking about this chunk of time right along in there. So what does it mean that these bars are pointed downward? Well, notice that they're downward from the zero axis, and the zeros line up. So that's a decrease in gas price, and if it's above the axis, it's an increase. So what happened? Well, in late 2001 and early 2002, they decreased from what they were a year before. Because if you look at the same time period a year before, in other words, it's not a seasonal fluctuation. You know, like when people have summer off and they go on vacation this summer, that's a seasonal fluctuation, and gas prices almost always go up then. It's quite the racket. But it's different from the trend of the year before. And then what else? Well, it's as a result, what happened? Well, notice how many bars are pointed down. There's an equal number of bars that are pretty high up there in green, which are the vehicle miles traveled. So gas price went down, folks hopped in the car, took some weekend trips, and maybe traveled more than they would have if their budget was strapped because of the price of gasoline. So an interpretation somewhere along those lines. And then in part B, in what time period was there a sharp rise in gasoline prices? Summarize the effect this had on vehicle miles traveled during the next 15 months. So the next 15 months. Well, if you look on along over here, remembering that gas prices are in blue, right in here was a tremendous jump in gas prices. Well, what does that correspond to? What time frame? That corresponds to early 2003. So essentially, gasoline prices went up dramatically as 2002 was coming to an end and continued to do so up to almost mid-2003. But during that time, the period vehicle miles of travel also dropped as gas prices rose. Big, sharp drop right here. Now, that makes sense if any of you pay for your own gasoline. If you have a driver's license and you have the luxury of a car, then if gas goes up, you think twice about just getting in there and going wherever you want to go because it's going to cost you. So families do the same thing. And then part C wants us to summarize the data corresponding the summer of 2003 through the summer of 2004. So here's 2003 summertime, and here's 2004 summertime. Way over here, they stopped in around May, I guess. Well, what happened here? Interestingly, we still had a really sharp rise right there and a bit of a rise right here in the gas prices. But unlike the trend that happened back over here, we did not see the vehicle miles traveled dip into the negative range. So it wasn't as dramatic a change. People probably got kind of used to the gas prices and got it better. If I could speak, this would be easier, and got it budgeted better in their monthly budgets. In other words, let's go to the movies one time less because gas has gone up. Instead of let's not go see grandma because gas has gone up. So you need to be able to look at graphs in lots of different ways and summarize the trends. Now, another kind of graph that you're going to encounter in this course is a semi-log graph, which means exactly what you think it means. One axis has a logarithmic scale, the other axis is linear. So just look at the numbers on this graph. What is going on the x-axis? Correct, temperature. What about it? Well, it's ranging from 24 to 29 degrees Celsius. You have to have an inkling, even though you live in the US perhaps, of what Celsius temperatures range. So room temperature in Celsius, where humans are happy, is about 25. And on the Fahrenheit scale, that's about 72, 74, 76, somewhere in there. So you have to have some kind of inkling about what's hot and cold in Celsius. And then what's taking place over here is that the median survival time, the MST, as it says right there, is given to us in minutes. So what is it the median survival time of? Brook trout as a function of temperature. So what happens generally? I haven't read any words on the left yet. Just look at the graph and tell me what happens generally as the temperature begins to increase. Typical answer I get from a student is it declines. And I say, oh, really? What is it? Define it. Pronouns are not your friend. Do not write on the free response portion of the AP Environmental Science exam in pronouns. It will not get you any credit. You would have to say MST, or the median survival time, decreases. In other words, fish die, and they die faster. All right, so now look, let's read the words. The points have been plotted on the graph has been completed by drawing a line of best fit. Now, in math class, you probably call that a linear regression, and you may have even run that on your graphing calculator. But labeling the axes and giving the graph a title is always important, so make sure that you do that. All those things are worth points. So note that in the title, the fact that logs have been used for the survival time data is indicated. So if you're going to do that, you need to say that. All right, and then along with the means for doing this, so a semi-logarithmic plot. So it's spelling it out right up here at the beginning. So the y-axis has been labeled MST, not log of MST, because the numerical values displayed along the axis are survival times and not log values. And they're times in what unit? Yep, minutes. Since it's impossible to take the log of a physical quantity, mass, volume, etc., when we deal with the logs of the numbers that measure these quantities, we can treat only the numerical value and not the unit of measure. So be sure you're aware of that. That's why we have just these numerical values along the temperature axis. But when you see a straight line, and you can think about the fact that this is declining as it gets warmer. Now, if this were time, we could actually calculate a rate. All right, another sample problem for you. This looks like a stock market kind of graph, doesn't it? Up, down, all over the place. The graph below shows the catches of Peruvian anchovy, anchoveta, from 1950 to 1999. So your brain should do a quick subtraction and say over a 49-year span. That's a lot of time. A lot of environmental impact can occur in 49 years. So this is one of the most important fish stocks in the world, and also one of the most notorious for its fluctuations, which are associated with El Niño phenomenon. Now, you may not have studied El Niño yet, but El Niño is a tropical Pacific Ocean phenomenon where warm ocean currents flow along the equator from the dateline and south off the coast of Ecuador and Peru. And this usually occurs around Christmas time for us. So it really does wreak havoc with certain aquatic populations. So we are asked to identify the period in which the greatest rate of decline in the fish harvest took place. Well, that means just a big old drop. So headed downward. For the 5-year period, give me a hint. For the 5-year period, calculate the rate of decline. Well, remember what rate is. Rate is any change in any quantity over a change in time. In other words, it's the slope when time is on the x-axis. Now, this doesn't say time, correct? But when you see 1950, 1955, 1960, can't you figure out the time in years from that data? So don't be a sucker. Don't think it has to say the word time. It just has to have time on the x-axis. So we want to do this in the unit of metric tons per year, which is good because they gave us million tons over here, and then show clearly how you determined your answer. Now the art is going to give for a little bit of forgiveness on the AP exam. So I see 2 regions of sharp decline. Do you see 2 regions of sharp decline? I do. That wouldn't happen to you on the AP exam. The art would be drawn such that it wouldn't be confusing to you. but I see that one of them is just ever so slightly more important than the other. This one started a little bit higher than this one did. Not a lot higher, a little bit higher. So this also is an uninterrupted decline compared to this little glitch over here in this other sharp downward trend. So I'm going to go with this one. All right, so rate equals the slope of the declining line equals the change in the population over a change in time. So read the graph. I would call that 13 million. And I would call that about 2 million. A little bit less, but we'll stick with round numbers. And again, you're going to have a range on the AP exam. It's not a defined answer. They're going to give you a reasonable range. Different eyes see the detail differently. And how many years did this take? Well, it didn't take 5 because it's a pretty sharp decline. So I'm going to go with kind of eyeballing this and call that 3 years. Again, they're going to have a range. So what is 13 minus 2? That would be 11 divided by 3 million years. Million per year, I should say. And so 3 goes into 11 how many times? Not quite 4. So 3, 9, 2/3, approximately 3.3 or so million anchovy. Oh, it's really more like 3.6. I didn't do my math right. Like 3.67. So I'll call it 3.7 million anchovy per year. That's a lot of little fishies. That would have a severe impact on food supply, huh? All right, let's do another. Sample problem number 4. You know that carbon dioxide is a hot topic, shall we say, global warming pun intended. According to atmospheric temperature and carbon dioxide concentration records derived from Antarctic ice cores, Earth's climate has undergone significant changes over the past 400,000 years. 2 graphs are shown below. The upper graph shows a variation in atmospheric CO2, and it says so right here. Then the bottom graph is graphing temperature anomalies. So both graphs cover the same time period from approximately 400,000 years ago up to the present. And the present was defined right there in the little copyright as being in 1999. So it's not all that present anymore, huh? But in the scope of 400,000 years, it's still pretty present. All right, so again, we have time on the x-axis. So they want us to determine the net change in atmospheric CO2, that's the red line, between 275,000 years ago and 325,000 years ago. All right, so where would 275,000 be on this graph? I'm again eyeballing it. Somewhere maybe along here. And note what happened. As the temperature spiked, pretend I could draw a straight line, the CO2 spiked as well. So that's going to be my 325,000 years. And then what else? 275. So where would 275 be? Wouldn't that be maybe about right in here? So if I do it faster, I might could do it straighter. There we go. That's not too bad. You would use like the edge of your test booklet or something like that to do a little bit better job than what I'm doing. So now there's my range that they're asking me for. So the net change in the CO2, I'm focusing on the numbers that go with these peaks. About I'm going to say it's going to be the rate of change of CO2, and that's going to equal to the slope, the change in CO2 over a change in time. I'm going to call it about 300 parts per million. And the other one looks to be about 180 parts per million. Left my zero off, that's not good. And what was this range? 275 to 325? Isn't that 50,000 years? So that's 120 over 50,000. So that comes out to be 0.0024 parts per million per year. Now, I did that with a calculator, okay? But you could do it longhand. It's just going to take you a few minutes. But again, when I just go find these, I'm not taking the time to make sure the math is really easy. But on the AP exam, you need to expect easy math. They have thoughtfully put together data that's going to let you be able to do that calculation quickly without a calculator. Numbers would be easier, in other words. And now what? Oh, we need to do the same thing for the change in temperature. So focus on the blue line this time. And we're talking about the rate of the change of temperature. And it's still the slope of the line. It's the change in degrees Celsius over the change in time, which I'm looking at roughly 4 minus the fact it dropped all the way down. I'm saying somewhere along in there, like about -9. And again, there's going to be a range. Don't sweat that you're not getting, your eyeballs are not seeing this exactly the same way mine do. Yours are far younger. Over the 50,000 years, it's the same time period. Don't have to figure that out twice, luckily. So that's 13 degrees C of change, right? That looks like a B. Try that again. 13 degrees C. Because 4 minus a -9 is the same as 4 plus 9, which is 13 over the 50,000 years. Once again, I cheated and used a calculator, and I get 0.00026 degrees Celsius per year, which you may want to put in scientific notation, or you can leave it just like that if you like. So 2.6 times 10 to the -4, if you prefer, degrees Celsius per year. Either way would be fine. All right, so that gave us two different sets of data on the same set of axes. All right, one more example. Can you make it? Can you make it? One more example. This is way more fun when you're doing this in class with buddies, and then you get to compare. Way better than listening to me. All right, an experiment is performed to test the toxicity of ammonium hydroxide. If you've ever smelled ammonia, smelling salts, that's ammonium hydroxide. It is in solution until you open the cap, and the minute you open the cap, ammonium hydroxide decomposes and gives off ammonia gas. So, using crickets as a test organism, crickets, I love crickets. I actually have a love-hate relationship with crickets. I am convinced that I built my house on sacred cricket burial ground, because in the fall I have white carpet downstairs, and you can walk down the hallway at any given time and there will be many, like upwards of 20 little black cricket carcasses on my carpet. At least they're not chirping all night long because they're coming in and meeting their demise, but I'm certain that they come to my house to die. So using crickets as a test organism, 6 different concentrations of ammonium hydroxide, 6 different concentrations, are prepared in separate containers, and 10 crickets are placed in each container. After 48 hours has elapsed, the number of crickets that have died is counted and recorded. The results of this experiment are shown in the table below. This is exactly the kind of thing that you're going to be asked to do on the AP exam. So when you look at data, you don't just look at data and read the numbers. You have to look at data, look at the numbers, glance at the numbers, think about a range on the numbers, and then think. What's the scoop on this heading? Concentration in percent. So it's percent concentration, and it varies from 100% to 0%. What increment did they use? Factors of 10. Agreed? 100, 10, 1, a tenth, and a hundredth. What effect did that have? Well, It's ammonia. You know it's stinky. You know it's not good for you to breathe. So the more concentrated it is, the more crickets die. And the data does show that. It's escalating in number of dead crickets as we move up toward 100. We're nearly all casualties at 100. And so the percent of dead crickets column is left blank. So you can quickly calculate those percents. What would they be? They made it easy on you because they gave you 10. So 9 out of 10 crickets is 90%. 7 out of 10 is 70%. 3 out of 10 is 30%. 1 out of 10 is 10%. Part over whole times 100. And 0%. That was easy enough. What else you want me to do? Oh, there's some weird looking graph paper. All right, this is semi-log paper. Get used to the way it looks. It's got this wide part over here, and it gets narrow, more and more and more narrowest. And it repeats, and it repeats, and it repeats. So when you see it oriented this way, this is your clue, obviously, for this to be 0, 0. But for you to now look back at your data and realize that these vertical lines, before they get big again, this is like your dividing line between the powers of 10. So we're starting at 0, and then we're going 0.01, 0.1, 1, 10, and 100. That's not so bad, is it? Now, what is this? What do these numbers correspond to? When in doubt, look back at your table. Concentration. Concentration of what? You may have to read again. It was ammonium hydroxide. Concentration. You can write the words, or if you've had chemistry and you know it's ammonium hydroxide, NH4OH. And then what unit is it in? It was in percents, because we had to figure that out real quick. All right, then what? What's on this other side? That's the easy one, right? Number of dead crickets. And 1 through 10. Let's see if we have enough. I'm going to count the little spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we need to plot the data. Okay, so at 0.01%, I had 1 dead cricket. Starting out 0, 0. So at 0.01, we had 1 dead cricket right there. At 0.1, I had 1 dead cricket. Not much fun yet. At 1, we had 3, so 3, 7, 9 were the rest of our numbers. So 3, 4, 5, 6, 7, and 8, and 9. So now we are to draw a curve through. Now, I'm not so good with this big fat pen, so you may be able to do a better curve than me. There you go. Don't go beyond your last data point, though. Let's see if I can join it that way. That's pretty good for me. All right, and then what is this? What they did not tell us in here is that this is actually a study on what we call LD50, lethal dose 50. So LD50 test for ammonium hydroxide on crickets is an excellent title for that. Now, what does LD50 mean? LD50 means the lethal dose where 50% of the population dies. Well, we had 10 crickets, agreed? So where would 5 have died? And where does that crash into our data? Right there. So I did 5, follow this line over, crash it into my data. Read down, what would that concentration be? Well, if this is 1, and this is 10, and that's 2, and that's 3, and that's 4, so it would be at 3.5%. That's when half of my crickets would die. Pesticides do a lot of these types of studies because we want to kill at least half of the population, but sometimes half of the population reduction is enough to keep that organism in check. We are not trying to create extinct species when we use a pesticide. We're just trying to not let it eat all the crops that we're growing for humans. So there has to be a balance there in nature. All right, well, you have survived. You have learned more than you ever wanted to know, and hopefully I have given you somewhat of a skill set to at least begin being able to grapple with the graphics. Until next time, I hope you have a great rest of your day.